Hi, my name is Naiwu, and today we'll be looking at Lab 4, Circuits and Capacitors. So the purpose of this experiment was to predict the behavior of circuits containing resistors and capacitors in both parallel and series circuits. It's also to measure the potential difference in the conventional current. And as a result, we see that the potential difference is 0 volts, while the time constant RC is 5.98 seconds. So some fundamental principles we need to know is Ohm's law, where voltage is equal to current times resistance, capacitance, which is equal to charge divided by voltage, the loop rule, which states that the overall voltage in a circuit will be zero, and the node rule, which means that one must go in, must come out. So we first start with the series circuits. First, we had to predict what was the current in these two ammeters. And we see that both of them are 0.02 amps at both locations. And the actual current was also 0.02 amps. And if you reverse the current, then it will become negative. Next, we try an open circuit. Our expected reading includes that the potential difference would be 3 volts, while the current would be 0 amps. And in actuality, it was that the potential difference was 3 volts and the current was 0 amps. And this is because voltmeters have an infinite resistance. The current will not pass through at all. So therefore, there will be 3 volts on one side with the batteries, while 0 volts on the other side with no current. Next, we calculate some potential differences using this graph. As you can see here, I'm not going to list them all out, but AB equals 3 volts, BC equals 0 volts, etc., etc. And with the loop rule, if we add all these up, it will equal 0 volts. So it follows our loop rule. And part of the reason for this is because the ammeters wouldn't change any readings at all due to their resistance being 0. So the ammeter does not affect the volts at all. Next, we looked at ammeter in parallel to a 100 ohm resistor. So the current will always skip over the 100 ohm because, well, not always, but the current will skip over the 100 ohms resistor because the current will always take the path of least resistance. Therefore, the potential difference across 100 ohms is 0. In this case, the ammeter in parallel, once the current gets to the junction, it will split. Therefore, that's the reason why the readings are 0.06 amps. And this supports the loop rule. If the resistance decrease, the current increase, vice versa. And through this, we also did some calculations. As you can see, the resistance at the 47 ohms, it was 47. 100 was 102, so it was around like the same place. The wire was 0, the ammeter 0. So basically, this calculation supports the fact that wires and ammeters have 0 resistance. Next, we looked at RC circuits. So we did two things. We charged up the capacitor and then we discharged the capacitor. So while we were charging things up, the light brightens and then it dims out when it's out. And it took 12.25 seconds for the 10 ohm resistor and the 20.37 seconds for the 20 ohm resistor. Discharging, it's the same observation. The light brightens and then it dims out until it's gone. In this case, the 10 ohm resistor took 11.85 seconds, while the 20 ohm resistor took 19.23 seconds. Also, with the discharging, the current was reversed. Next, in using the previous RC circuits, we plotted out some graphs. So basically, at each interval of time, we measured the voltage, and then we took the natural log of the voltage over the initial voltage. So as you can see here, it makes a pretty clean linear equation. And using the slope, negative 0.167, we can find the time for the RC, which is 5.98 seconds. So question, what if you're doing this lab in real life and use actual ammeters instead of an ideal simulated ammeter? What's different about a real ammeter and how it would affect the circuits you hook up to? Well, with real ammeters, there will always be resistance because it's not ideal. Therefore, the current measurements would be lower. what were you doing in this lab in real life? Or what if you were doing this lab in real life and use a real battery to charge a real capacitor with no resistors and current? How quickly would our ideal model, predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. Well, all components in real life will have some resistance. Therefore, the capacitor wouldn't be instantly charged. Instead, it would require some time for the capacitor charge.